Okay, so we've now had the academic 2 minutes, so I think we'll go ahead and get started. So, welcome everyone to this top webinar number 39. So today the focus will be on a recent review paper by, sorry, uh, by Eddie Vatbo and co-authors. And today Eddie will present a sort of an introduction or a very quick overview of the review paper, and then afterwards we will be open to a discussion. So if you have any questions, feel free to write them in the chat, or save it until the end, and we can unmute and talk to each other. So this time it's a little bit more open than the last few times, but we'll give this a shot. So without further ado, Eddie, I will stop sharing and then you can share your screen.
So, yeah, thank you very much for the invitation. And this is, well, I will talk about the review paper where me and my co-authors, it's a field that we're very interested in. We have read a lot, and also in the paper there are many, many references. And in my presentation now, I will have 0 references, but more focus on, well, trying to give you my sort of view and my interest on this paper. But before starting with that, so thank you number one to all my co-authors, Martin, Mario, Khan, and Abbas. It's been, it's joint work. It was a pleasure working with you. We had lots of fun, lots of discussions. And also, in addition to my 4 co-authors, I would like to thank the 4 anonymous reviewers. They did an excellent work, and I think based on their comments, we could really gut out a much stronger review in the end. So much fun. So, but let's get to it. So the review is on, well, how to take care of boundary effects, or or look into boundary effect dominated problems using the material distribution or density-based topology optimization. And first of all, in many engineering systems, they are not only governed by bulk behavior, but in many cases, dominant physics occur at interfaces, near boundaries, and in thin layers. So classic examples on this is sort of where we have a domain and we have loads or fluxes acting on evolving interfaces. Transport dissipation happen in sort of layers around the boundary, and also, well, where we have some impedance effects, so that are affected boundary phenomena. And in all of these cases, ignoring the boundary effects and just looking at the bulk will yield, well, we can of course use material distribution to optimization anyway, but if the model or the partial differential equation we have do not take into account these effects, the designs will be performing well, but not for the true governing physics. So this is the whole idea why we started getting interested in this and looking into various problems for it. So, and just trying to define, okay, what do I mean with the boundary effect dominated problem? So I put up like 2 major points, or 4 depending on how you count. So number 1 is the physical response depends critically on the position of the interface and the geometry of these boundaries. And the boundary itself, well, it depends on the design, and it's an active part of the governing physics. So the key consequence here is that the methodology for solving these optimization problems must be able to first identify, represent, and use this evolving boundary correctly. So this is sort of the whole background for any optimization you want to do for these problems. And also a graph from the paper, sort of, why these problems now? And looking at the growth of design optimization problems that involve design depending pressure loads, boundary layers, as well as coated structure over the past 20 years. And here I know that sort of the coated structures, it's sort of not really boundary effect dominated, but since the techniques for coated structures sort of translate over, we decided to include this in this review as well, because essentially the story here is that the same techniques occur across all types of physics, but of course when you start studying one problem, you may be able to tinker a bit to get this better. So In essence, this graph tells us that boundary effects are no longer niche problems. They come in multiple application areas, and the challenge here is that the standard assumptions that lies behind density-based optimization, that starting from linear elasticity, doing compliance minimization, these sort of do not really perform perfectly without some extra special fixes. And people have been acknowledging this and working on boundary effect dominated problems for at least over 20 years, even though we just limited this graph to the last 20 years. Right? So if I look at standard material distribution topologization, so what we have here is we have a distributed field, which I will call alpha, that is in 0, 1. And this here distributed field will enter into the partial differential equation and define various physical quantities. So the geometry is implicit, and traditionally this has been developed for, and it works extremely well for, when we have bulk dominated problems and then boundary conditions are of Neumann's or stress-free type, so they're natural boundary condition that just sort of disappears, and when we put up the variational form, it all falls out naturally. However, this sort of intuitive description of just extending the domain of integration becomes problematic when the physics do depend explicitly on the boundary, such as for pressure loads, convection, or when we have impedance boundary conditions. And so depending on how you view it, the difficulty is not the background optimization, but that we actually have this implicit the definition of the geometry as well as the boundaries. And with that, I'm moving away from the general introduction to the classic view on this. So if we look at the history, so fictitious domains methods is that we have a body that we're interested in that is embedded in a bigger domain omega, so typically a square or something nice. And then we solve the governing equations inside omega, and the geometry is encoded either via penalizations or distributed material coefficients. And the key idea is that the geometry here comes in to the partial differential equations through some coefficients, but it's not explicitly tracked. And looking into these ideas, there is much more in the article, but they have emerged independently and in multiple communities, can at least be traced back to the 50s. It comes under different names depending on the field. So fictitious domain methods, immersed boundary methods, or domain embedding techniques. But in all of these even if the background is in mechanics, fluids or so on, it's driven by similar needs. We want to model complex or evolving geometries, but we like to solve problems on fixed, often Cartesian discretizations, because this is where we, from a compute perspective, can get much speed. We have a structure that we can utilize when solving this. But nevertheless, the idea of embedding a difficult domain where the physics happen into an easier domain and solving the problem there is a recurring idea that has been rediscovered over and over again. And yeah, I will repeat again. So why does this actually matter for topology optimization? And if we just look at this from the most basic problem, the standard model problem, compliance minimization in structural mechanics or linear elasticity, this is inherently a fictitious domain method where the design field that I call alpha consistently, that there is typically called rho, this encodes the physical body, but we never look at where the boundary is. So the formulation of fictitious domain methods naturally support topological changes and large design freedom, right? And this is indeed one of the core strengths of this method, right? So we can essentially get an unlimited design freedom. However, it also comes with an asymmetry on how boundary conditions can be imposed. So starting from the easy case. So I will just claim that Neumann or stress-free boundary conditions, they are easy, right? They arise naturally in the weak form. After we have discretized the problem, we do not need to care. It comes for free, right? So It's very nice. We get stuff for free, and taking a free lunch, just do it. So there is such a thing, at least in this case. However, if we go to, say, Dirichlet type conditions or Raban conditions, they require additional mechanisms. So if we have Dirichlet conditions that prescribe field values on the boundary, however, the boundary is implicit, so we somehow need additional strategies to enforce these conditions. So common approaches is we'll use penalties to get the boundary values where we want them, Lagrange multipliers, or Nietzsche type formulations. And by using these approaches, we can extend the fictitious domain framework to solve to evolve and solve other problems within it. Of course, not all of these are convenient or robust in gradient-based optimization, but as a start, we can extend fictitious domain methods. And another personal view here is that, well, many people you view penalties. We push something in that, or we add something to the formulation that pushes the field to be where we want to. But penalties, they are not just numerical tricks, and they often correspond, to meaningful physical models. So if I look at electromagnetics and I push the conductivity higher and higher, so like in the extreme case, I will approximate a perfect conductor, which then would set the field value to 0 in that case. And the same thing if I have a fluid mechanics where I have a high drag. Well, look, so now I'm not sort of moving away from the fluid region and entering a porous or solid region. And these interpretations are crucial and have been crucial to solve boundary effect dominated problems. And looking into this sort of Navier-Stokes or Darcy penalization, so just putting up here the equations for velocity, what one typically sneaks in that is not in the standard case is this alpha times u. So if alpha is 0, okay, this term disappears and we're back to the standard fluid equation. But if I push alpha up to become bigger and bigger, and in the limit as alpha goes to infinity, this term here will essentially dominate everything, and in the sort of parts where alpha is close to infinity, u must be 0, since the other terms you can just neglect these. And then, of course, if we want to do optimization, we want to have a smooth transition between the fluid and the solid region, and this is where the art comes in, like how to actually tamper this alpha in order not to get into too many numerical issues. Nevertheless, the interpretation here is that there is a boundary, but it's actually enforced by this material penalization that just enters as a term in the body. So there is no nothing happens on where the interface is, but we do have a penalty inside the solid body. So of course, by just mentioning this, there are still things that fail or that is not as easy, right? So the penalties are good to handling homogeneous Dirichlet condition, but if we want to have pressure loads on evolving surfaces, convection or Raban or impedance conditions, we somehow actually must take into account the location and the geometry of the boundary. This must be known, but the good news is that we can still take care of this within the material distribution framework, but a bit of extra effort is needed. So the transition here is that, well, we go from our implicit geometry, where we have the fictitious domain formulation that sort of act as the core, right? But as soon as, or the more difficult boundary effect dominated problem we look at, we need to add more and more structure into these fictitious domain method. And this here naturally leads me to want to talk about filtering and image processing techniques and interface recovery. So there's also a rather big part on how can we actually get from this implicit geometry description and what can we extract from this one. So filtering is indeed a central part to get, or of the success of material distribution topology optimization methods. So here we have our design, which is represented by our function alpha, where at each point x we have a value between 0 and 1. So the geometry is implicit, but if I look at filtering traditionally, if you go back to the 90s, this was introduced to remove checkerboarding and avoiding mesh independence. So these are sort of the two classic issues with topology optimization. And it was early on recognized that, well, if we just do filtering, it sort of clears these two problems. But since the 90s up to now, filtering has evolved into a primary mechanism not only to take care of these problems, but also to get size control. And it does play a pivotal role in interface identification and control. So here comes a bit more on the filtering and the background. So so as I said, it has had an early role and a modern role, and filtering is today a key part of the method, and also the development of new methods and new filtering strategies, they do go hand in hand. So, and one sort of interpretation that I like to take is to view the design as an image. So now I will just take, okay, I have my alpha. I will discretize this to an alpha h that in each pixel is a constant. And this is sort of the same ideas you have with standard digital images. You take your domain or your picture, you put it into you do it into pixels, and for each pixel you have one single color. And there has been lots of work in the image analysis community on this, and this is sort of part that the material distribution topology optimization community has been able to capitalize on. So in the generic sort of base version, if we take a linear filter, so if I take my filter operator f, it takes this function alpha, and if I want to get what this one is at x, I just take alpha and then I push this through a convolution with the normalized kernel. And in layman's terms, the support of this kernel defines a minimum length scale. And the effect here is that it smooths the design, it introduces great transitions near the interfaces. So we sort of have a blurred representation of where the boundary is. Nevertheless, the sort of linear filtering was a key step in the, well, early parts of this millennia and also in the late part of the 90s to why the success started snowballing. Of course, it did not take long before people realizing that, well, I want to have a sharp interface. And the easiest way to get this on is that, well, we do our linear filtering, and then we apply some nonlinear function to this pointwise. So normally this g of beta n is a smooth approximation of a shifted Heaviside function, keeping the notation to what is standard in the community. The parameter eta controls the location of this transition region, so essentially where, well, we want to do not the thresholding or projection, but where we want to transmit the quickest. And beta is a parameter that controls how sharp this approximation is. So if you push beta to infinity, then this g beta of eta goes to the proper Heaviside function. But for any sort of choice of these parameters, that is where we do not have pushed this continuation parameter to infinity, this mapping, I would say, is a smooth modeling choice. That's sort of not really a projection, but it's a smooth modeling choice that gives us a sufficiently sharp image so that we can get our nice things. The next part in the sort of evolution of filters is to move over to morphology-inspired filters. So in morphology, mathematical morphology, so you want to probe and get information of a domain, in this case represented by my design alpha, by probing it with the ball B. And the two basic things are the erosion and the dilation. So the dilation, you just take a pen shaped as B and you move it around your alpha field, and then you just color in whatever. The erosion is the dual operator, so you take a pen shaped as B and you sort of move it around in the complement of your design, and you just erase out whatever you can. And if you do an erosion followed by a dilation or vice versa, we get these sort of opening and closing operators. Initially, this is sort of defined using min and max operators, but for natural sort of causes, when we use this for optimization, we want to use continuous approximations of these operators. And these filters are sort of naturally suited for boundary and an interface or boundary strip manipulation. And next, sort of now I'm moving away from the sort of filters based on convolution to PDE-based filters. And here I will just say that I denote the field by L, and the capital L is my linearly filtered version of this. And we can define a filtering here by saying that, well, my filtered field L solves this strongly elliptic equation, where this R here is a parameter. The good thing with casting this as a PDE is that we have highly efficient solvers available. You can do multi-grid, get this really quickly. It naturally extends to complex geometries, and it's a particularly nice and attractive problem for large-scale problems. And this parameter R is indeed correlated with the feature size you get. So it sort of shares many features with the other filtering, or with the convolution-based filtering. And a unified view that I like here is that many filters, or essentially all filters that I've shown in this presentation, can be, or at least in the base, written in this form. So I do not take and do my convolution with alpha directly, but I apply a smooth function pointwise. Then I do my linear filtering, and then I do and apply another invertible function. And this framework here unifies linear filters, the morphology-inspired ones, the PDE-based ones. But this is and this can of course be extended into making just a large sequence of filters. So if I take and apply many of these sort of FW mean filters, I'll just write out this as a structure. So I start with taking this nonlinear thing going on alpha, then I do my convolution, which is a W, and then I just alternate this. So these phi1 is F, phi2 would be the first G and then compoused with the next F. But if I look carefully at this structure here, this is an alternating linear averaging and nonlinear activation step. So this is exactly the same structure as we have in a simple feed-forward network. So one way to interpret the filtering that we do is that this is a pre-trained mapping from design variables into a physically meaningful geometry, which sort of couples nicely to what we actually want to do. Right? And why does these sort of cascades matter for boundary effects? Well, cascades enable us to do explicit extraction of the interfaces, not just like an erode or a dilate, but we can combine these different filters that we have. The first thing that I mentioned now, the combo of dilate erode, can extract a boundary strip with controlled thickness. We can do multi-field representations, so we can have get different parts out if we have multi-material topologization. And the good news with these things here is that we do not need to track the boundary explicitly, and this is indeed a cornerstone for these boundary effect dominated problems. And next, I would just like to mention a few words about how these IDs can be used to treat design-dependent boundary physics, not just going in on how they are treated now, but also trying to give a little bit of IDs on the core evolution of the methods. So again, boundary-dependent physics, same motivation as earlier. Many of these problems become challenging because the boundary is implicit, right? If we would have known where the boundary is, so say if we would use the level set discretization, we can just put in the boundary conditions and go nicely. But what I will talk about now are various problems that differ in physics. They share a common structural difficulty, and also we can sort of get through this one using similar IDs. So one of the first problems that people started looking into in the community that actually has something, well, design dependent on it, are the design dependent pressure loads. So the still linear elasticity, but where the load actually depends on the location and the orientation of the boundary, right? So where the boundary is, we want to put our sort of traction forces and so on. But the early approaches here, you started off with, well, let's do a explicit reconstruction of the pressure phase. So we have our design, and then we pull out the pressure surface and explicitly track this one. Later approaches were more implicit, where we tried to get the boundary indicators out from filter design fields, and then putting these filter design fields into the variational form. The key idea here is that we take the reformulation of the pressure effects inside or on the boundary into a nice differentiable distributed section. So we sort of smeared out where these things happen into a sort of tubular neighborhood of around where they should be. And a very similar problem is in my view, is the heat dependent or design dependent heat flux and convection. So the heat exchange depends on which parts of the boundary are exposed. So we do not have this over all of the boundary. Also in this case, the conceptual progression was very close as for pressure loads. So if the idea is out there, you can see, well, which other problems can we attack? So starting off with explicit identification of exposed boundaries. And then later on, but the field or people in the field started to using these surrogate boundary indicators from filter design fields. And the key idea here is to reformulate this convected heat flux in a differentiable distributed session. So in my view, same, but different. So, or in other words, the two problems do share the same structure, but physics are different. So for the pressure loads, where we have the boundary localized forces, and for the heat flux, we have boundary localized heat exchange. And of course, in both of these cases, so for pressure loads, the direction and magnitude depends on the interface of the geometry. And in the heat flux, well, these coefficients will depends on the exposed surface. Is it exposed or not? The physics are different, but we still have the same underlying problem. A third sort of classic problem in optimization. So now we have moved. So the two previous problems that I talked about, the design-dependent pressure and as well as the heat exchangers, they are turn of the millennia. Coated structures, I think this more started around a decade ago. And the cool thing there is that, well, these coated structures, they introduce, explicit boundary layers at the design's boundary, or in some sense, right? So the challenge is not only where the boundary is, but how thick it is. And to extract this one, so the early IDs were that, well, we take our alpha, we filter it, we look into gradients or isocontours of this filtered field, and then later on one started to look into more filter-based construction of finite width boundary strips and doing direct control of the coating thickness and separation of length scale. So we're actually getting out. So, and here is just sort of one of these classic approaches where we take our field A, filter it, compress it, filter again, look at the gradient of this one, and then get a boundary indicator out that directly depends on the design. And sort of if we increase the boundary complexity, so if we're just looking at, okay, well, in the pressure loads, we only cared about the location of the boundary. And heat transfer, well, we looked at, okay, which parts of the boundary are exposed. And in coatings, we look at, now we look at the boundaries that do have a thickness. And the shared difficulty here is that, well, okay, we need to identify the boundary. We need to identify interfaces. And in some sense, we need to sort of have a controlled boundary representation. So these are all, I'd say, from a boundary identification perspective. Of course, similar techniques can be used, but and then applied to across all types of physics. But of course, this motivates a more advanced treatment of boundary layers. So which problems can we now solve, or what are the next steps? Is sort of a natural way to do this, right? And looking at problems with layers. So this is one of the more sort of semi-new things in the review article, that we sort of consider an interface gamma that splits our omega into two subdomains, omega 1 and omega 2. And in many applications, layer phenomena occur in the neighborhood of this boundary. So where this sort of characteristic length scale of this layer is much, much smaller than the bulk. And the image just sort of illustrates, well, we can have boundary layers both on the inside and the outside of the interface, depending on which physics we're looking at. And it could also be that the phenomena are graded throughout this layer. And yeah, so why are layers particularly challenging for material distribution optimization? Well, so if we look, say, go to the extreme, take Navier-Stokes. If we want to do an accurate simulation of Navier-Stokes, it requires an extreme mesh refinement close to the boundary. And in material distribution topology optimization, where our sort of boundary gamma evolves, and we do not have this explicitly tracked, right? So we cannot really hope to get this layers fully refined. Local mesh refinement breaks because in the fictitious domain philosophy, we should not know where the boundary is. It should just sort of be encoded by coefficients that enter the equations. So the core difficulty to be able to solve more interesting or more challenging problems with layers is that these boundary layers or the effects of them must be accounted for without explicitly resolving them. So we need to sort of encode those within the variational form setting. So the key modeling idea here is that, well, we have a boundary layer, but in many cases, these can actually be replaced by boundary conditions that take care of its effect. And then, so instead of resolving the layer, we represent its effect by a boundary condition at gamma, and then the bulk problem remains somewhat nice in omega 1 and omega 2. And then the layer physics enter through an additional boundary term that we need to take care of in the variational formulation. And the full principle here is that the model, the influence of the model of the layer on the surrounding field, this is what we want to model. We do not want to resolve the layer itself, but we want to know, okay, what are the primary effect of this layer on the surrounding field? And then if we can resolve this, then we are good to go and do design optimization. So canonical examples of where we have this is sort of in electromagnetics. If we look at high frequency currents, they are typically confined to a very thin skin layer in conductors. The skin depth here, or the depth of these currents, are orders of magnitude smaller than the wavelength. So going in to resolve these would actually increase compute time a lot. And for acoustics, if we look at sort of hearing aids and so on, we do have, well, viscous and thermal boundary layers that form near a rigid wall. And dissipation is dominated by these thin layers in the fluid adjacent to the boundary. But in the bulk, we essentially can ignore losses. So in both these cases, resolving the layer directly is impractical, it's extremely costly, but which makes this impractical in an optimization setting. So instead, what we aim for, or what the field is aiming for, is to resolve or to model their effect on the bulk by imposing boundary conditions. And these sort of impedance style boundary conditions are designed to capture the effects of boundary layers. And essentially what they do is that they relate fluxes on the boundary to boundary values of the field. And in a generic condition, the resulting boundary layer couples the bulk PDE with the boundary operators through a boundary condition. In this case, where this Z of U is potentially a differential boundary operator encoding the layer effect. So we sort of have a partial differential equation with another partial differential equation acting as a boundary condition. So it's, from a mathematical modeling perspective, of course, it goes more difficult, but it is possible to solve this without resolving gamma, because we have this. Yeah, so in this case, there is definitely a cost in solving it, but it's a lower cost than fully resolving the boundary layer. So as I said, so just the same thing here as many times earlier in the talk. For both electromagnetics and acoustics, the bulk of the variational form is unchanged away from gamma. We can ignore these effects further away, but the layer effects, they do appear as additional integrals over gamma. The boundary operator is different in the two cases, so it's an algebraic operator if we look at the skin effect, and it's a differential operator if we look at the viscothermal acoustics. But in the insight here is that seemingly different physical problems lead to very closely related variational formulations, which means that we can treat them within a unified framework. So this opens up for a nice coherent treatment of the problems. And if we do have fixed meshes, so in material topology optimization, the boundary is never explicitly available. But so the boundary integrals, they must be expressed on a fixed mesh because we do use the fixed mesh. And this is achieved by using boundary indicator functions. So normally we just sort of take our design and we resolve this on our mesh by an element-wise indicator function. And what is sort of added to take care of boundary effects is that we add a function that lives on the element edges or faces. And this is one can, for example, look at the jumps of the indicator alpha. So if I have a 0 and a 1, then I know that, okay, there should be the edge indicator function here should also be a 1. And if I have the same on both sides, it should be 0. So this is just sort of a hand-wavy thing of how do these boundary indicators look. But yeah, so the implications for the topology optimization, well, the good news is that by putting all of this together, this has enabled topology optimization for layer-dominated wave and transport problems. We avoid the nasty local mesh refinement near the evolving interfaces, and it sort of naturally integrates with standard material distribution methods. So the good news and the key message here is that these boundary layers can be treated as boundary operators within our standard fixed domain optimization framework. And now comes the time for my sort of concluding discussions here. So to repeat from what I said from the start, boundary effects are central, and the boundary effect dominated problem arises across multiple physical domains. And the issue with standard material distribution topology optimization is that boundaries are implicit. However, the governing physics often depends explicitly on the boundary location and structure. So boundary effects are not special cases, but they recur as a central challenge in topology optimization. And we have started to come, or we have already come a good way into resolving this type of problems. The reoccurring methodological themes that are here is that what we need is accurate boundary identification. This is essential as well as non-trivial. Filtering has sort of evolved from playing the role of pure numerical regularization and length scan control to also be a core part in the interface recovery and boundary extractions. The indicator functions based on gradients, jumps, or morphology or image-based methods, these sort of recur across applications and have sort of evolved in parallel over multiple application areas. And by using impedance and boundary operator models, we should be able to extend the applicability to even more interesting or challenging boundary dominated problems. So of course, we're not all the way there. We have not solved everything. But the remaining challenges is that, well, we won't have a robust and accurate boundary identification. This is still somewhat of a bottleneck. So it comes with a cost. The high fidelity physical models, they do increase the computational cost. And by just looking at, okay, what type of problem are we looking at? What are the trade-offs? So of course we want a sharp interface. But to get the sharp interface, we need to increase the nonlinearity of the operators we have, which indeed sort of harms the differentiability of the complete mapping, which makes the optimization more difficult to solve. And also the nicer interfaces or nicer, more smoothly varying things, varying fields, makes it easier to create scalable and robust numerical methods. And another remaining challenge is that so far there are not that many standardized benchmark problems, which indeed complicates comparison and validation. So the last and sort of contribution of the review article is that we sort of suggested a few possible benchmark problems that sort of, and the idea there was that these benchmark problems must test boundary identification and evolution, coupling between geometry and physics, and the robustness to a changing topology. So the first one here on top is, a standard MBB beam, but with the pressure loading. So the pressure comes normal to the boundary, and the question is, well, how should this one be designed? Problem 2 is a standard MBB beam, but with an added coating of a certain thickness. So this could also be used to test your methods. Third one, I think this is the acoustic black holes. We have an incoming acoustic wave from the left. We have a design region, and on the boundaries here we have viscothermal losses, and then you sort of want to design a dampers. We want to damp everything. The fourth one is you have an input and an output, and we have a sort of, this is the viscoacoustic case. So we have fluid, and here we want to put some the deformable solid, and the idea is, well, we want to minimize the field in this target area. And the fifth possible one is cooling problems. We have a thermal problem modeled by the Poisson equation. We have an incoming heat flux at gamma Q. And at the design's boundaries on this gamma S here, we have Newtonian cooling. So we need to track where the boundary is to impose this cooling, and then sort of see, well, what type of designs do we get out. So these are a few possible suggestions for future benchmark problems. I do not know which ones are the most challenging or where the field will go, but at least having a few suggestions up could be a good start for discussion. And then my final perspective is sort of that boundary effects have defined a new frontier in topology optimization. The progress requires us to do boundary aware modeling and get scalable algorithms, because as time progresses, people want to have cooler and cooler designs, more difficult physics, preferably everything in 3D. But the material distribution methods remain powerful, but we must sort of extend these thoughtfully, thinking through, okay, what are the next natural step and which difficulties to add next. There is lots of interesting problems, and boundary effect dominated problems are, in my opinion, central to many future advances in physics-based design optimization. There are other things to consider as well, but this is indeed one of these things that I intend to look more carefully into. And with that, I say thank you all for your attention. It's been happy to be here.
Thank you very much, Eddie. That was a great overview of a large body of work and an evolving field, as you mentioned. So I, of course, suggest everyone to go look at the paper. It's open source or open access, so you can go read it, everyone, no matter where you are or where you come from. So we are now open for questions, so you can just go ahead and unmute yourself if you have a question. So we have one question in the chat. Any tips for reading up on the morphological approaches?
Oh yeah, so that's, well, you can always go back to the first suggestion came from let's see, Ole Sigmund, so his paper from 2007, and then we have the Svanberg doing based on Pythagorean means, and then of course I also must sort of make tips of my own paper. So together with Linus Hegg, I wrote a few papers on these FW mean filters. But there are, of course, others as well. But I can, if you send me an email, I will be happy to share those with you.
Yes, and then Julian has a question.
Yes, thank you for the presentation, Eddie. Very, very interesting, and the paper is also interesting. I'm interested about your point about the benchmarks, because the point about these diffuse representations of the boundary in, let's say, density-based methods, for instance, not giving us an accurate representation of the boundary for the purpose of the simulation. That's, absolutely correct. However, I wonder to what extent, because, there is always an extent to which the topology optimization will give you a good design because you get directionally good information, even if your simulation is not highly accurate, right? And so I wonder if in your review, you came across an example in which having an inaccurate boundary gave you an entirely different topology than if you didn't.
That's a good one. Now I need to think. And also, well, I see that some of my co-authors are here, so if they would like to step in and sort of help me out. No, so
That's a good question.
yeah, no, but I know that for some of the yeah, thank you, Martin. Yeah, I was going to say something about the acoustic cases. You can mention the work with Abbas, I guess.
Yeah. I was thinking, can you hear me?
Yes.
Yes.
Yeah. I was thinking about a case when it's a partial answer, of course. So I mean, if you have a possibility to have a very, it's a big difference how the resolution is. So I think that is the first thing that we have seen, that when we have possibility to have very complicated shapes, we can get extreme changes in the optimal. So that is, I guess, nothing new, that you can have the resolution of the boundary is very important to get. You can get very different results if you allow for complicated shape or not. That's maybe not the answer to your question directly, but at least that is one part of it.
I think also it might depend on what you mean by an inaccurate boundary, right? So
if it's
so for
one thing is the
instance,
representation and one is the physics, right? So if you do
exactly,
so
yeah,
if you add
that's true.
more physics on the boundary, so like the viscothermal losses in acoustics, or if you include them or not.
That's
so
extremely important.
For small devices, it's extremely important. For big devices, you can ignore it safely.
Yeah.
Right. So it's problem dependent.
Yeah, and I'm also thinking for the heat transfer case for the Newton's law of cooling, you will see a difference whether you have it or not, right? So including those boundary effects makes a difference. But maybe Julian, can you elaborate on what you mean by inaccurate boundary? Maybe.
So I think what I meant was, whether you're capturing accurately, meaning, quantifying, let's say for the let's say in the case of the Newton convection, whether you're accurately measuring that from the solution of your Navier-Stokes equations using the Brinkman penalization, right? Nevertheless, the topology optimization could give you a directionally good design, right? Even if that prediction of the convection heat transfer is not accurate, right? So I think it would be very beneficial for the entire community to identify a benchmark for which, if your prediction of the physics near the boundary is poor, then you get a completely different topology, right? So that then it can serve as a test, right? That you can say, you came up with a new method that should handle boundaries, and if it's not capable of solving this benchmark, then that's already kind of not a good thing.
Sure.
I mean, maybe I can add this comment that if you think about like inaccurate boundary conditions compared to more accurate ones, especially for the acoustic case that Eddie just talked about. So we have already added this as some sort of a benchmark that for wave focusing, especially when you want to focus the acoustic waves into a very small region, then if you don't consider viscothermal losses at the boundaries, which means that you simplify the model, you simplify the boundary condition that you're considering into just sound hard boundary conditions, then the optimizer will actually very likely ended up in a local minima, where when you do a proper simulation of that optimized design, you will notice that you get significant losses at the boundaries. So considering those proper or more accurate boundary condition is quite important when it comes to the evaluation of the performance of the optimized design. And if you use an inaccurate boundary condition, then probably the optimized design that you will end up in will actually perform poorly when you do the more accurate simulations. Yeah.
Thank you, Bas, and thanks everyone.
Yeah.
Thank you.
I have a question. So I've worked a bit with these kind of problems myself, and and also I read the paper, and there seems to be many different ways of doing this, right? And some look at, you know, gradients, some look at jumps between elements, and there's a lot of different ways of doing it. Do you see, sort of looking into the future, is there some kind of unifying method that you think is more promising, or what, based on sort of the overview?
I see a few different ways to do this, but I'm currently, you know, a fan of these phase-based indicators, and then also not just doing the jump, but doing the jump squared or the jump to some power. To sort of, because otherwise, if you have a sort of a boundary that is smeared over many elements, if you just take the jump, if you just sum up, the variation will be 1. But
Right.
if you take the jump squared, for example, having like 10 steps with 0.1, then you will only get like 0.1 in total of the effect. But if you press it together to sort of a direct jump from 0, 1, you get all of the effect of this boundary up. So it sort of, in that sense, acts as a, well, in some sense, as a penalty to promote sharp interfaces as well.
Yeah.
I, as I said, I have no proof of stuff here. It's just a feeling that it sort of acts as, you know, something that accelerates the optimization and pushes you towards a sharp design as you want.
Yeah, and I think
But this is only when, you know, when you want the boundary effect, where this is something you're after.
yeah.
In these cases where you want to avoid it, maybe, you know, smoothing it out could be a way of cheating it away, right?
Sure.
With such a thing.
Yeah, I mean, we're doing the same for these turbulent wall functions now, also using a penalty on the gradient, or a power of the gradient. Or it also sort of focuses the boundary condition a little bit, making it a bit more accurate.
It's sort of, it's a nice idea, and I think that the same idea will, it's sort of, the time is right for it, so it will pop up in many different ways now, and then hopefully it will converge.
Yeah.
So I guess that, you know, similar to, you know, when people start looking into penalties for the compliance case. So there were lots of different, like, material interpolation functions introduced at some point.
Yeah.
But yeah.
Yeah.
I think we have a fun time ahead.
Yeah. Yes. Do we have any other questions from the audience? Let me just double check if there's any questions on YouTube. There are no questions on YouTube. Okay, well, last chance. Okay, and last chance to you, Eddie, to say something clever if you want.
Something clever. Yeah. Thank you once again. Thank you all for joining, and yeah, we're perfectly on time. So
yeah, it was very good. And just before everyone logs off, I just wanna mention the next 3 webinars will be, again, tutorials, this time on the level set method, or level set methods, and presented by Grégoire Allaire and Charles Dapogny, and they will be in rapid succession in May 13th, 20th, and 28th, and go to our website. There should be links to the Zoom registration, sign up, and you can also sign up to the email newsletter, and you will get a reminder.